Just video for the example. I think it's better to navigate later. So T and B, R is given. The first step is to find R prime. So I will do that. If R is given as cosine T, sine T, and T, to find unit tangent, I need to find R prime. So let's find R prime. R prime will be cosine gives you minus sine. Sine gives you cosine, T gives you 1. Okay, now I can find T, which is R prime divided by the size of R prime. You can find the size separately if you want, but in this case it will not be that hard, so I will do it right away. Let's do that. Let me change the color into green. Green is T. T takes the vector, which is the derivative of R, minus sine T, cosine T, and 1. That is tangent already. So R prime is tangent. But the unit tangent says, I don't want to have the size of it. What if it's huge? It's kind of messing up with my calculations. What if it's this big? I don't want to have this big. Or what if it's this tiny? I want to get rid of the size. And that's why tangent is called unit tangent, because it's convenient. We get rid of the size. So the size of that vector is what? Square root of what? You remember the magnitude? Square root of sine squared plus cosine squared plus 1 squared. Sine squared plus cosine squared gives you 1, so it's square root of 2. Should I write it down carefully, or you got it? I guess, let's see. Do we want to submerge it? Oh yeah, let's write down once. Sine squared plus cosine squared plus 1 squared, like so. That's a square root of 2. And now you can simplify. You can put it in front of the vector. So it's going to be 1 over square root of 2. This is what this number helps us to get rid of the size of the original tangent vector. And then I will have green minus sine T, cosine T, and 1, like so. That is the answer for T. Put it in the box. That is a T. Now we need to find N. N takes derivative of this T and divides by the size of that derivative. Isn't it interesting? People are like, no, it's not interesting. I'm tired. Let's go home. Let's continue. We have to continue. So N is, let me change the color into blue. I guess why not? Let's differentiate T. Derivative of T now is 1 over, let me do it like so, is 1 over square root of 2. Vector minus sine gives you minus cosine. Cosine gives you minus sine. 1 gives you 0. Like so. T prime. Do you agree about T prime or not? T prime. I'm just differentiated. Remember the constant, if it's multiplied, it stays. The derivative of A times cosine is A times minus sine. So it makes sense. Now we need to divide by the size of that thing. The size of that thing is 1 over square root of 2 times the square root. Cosine squared plus sine squared. Cosine squared plus sine squared plus 0 squared, right? That can be simplified as just square root of 1. So it's conveniently that these constants, 1 over square root of 2 and 1 over square root of 2, canceled out. So unit normal vector became pretty nice looking. It's just minus cosine T, minus sine T, and 0. You could actually factor out minus, but you don't have to. That is normal unit vector N. So we have T and we have N. Only B left to find. T and B. Let's do that. That one will not have enough space. So let me summarize what I just did. I found N as T prime over T prime. To do that, I found T as R prime over R prime. And when I say over, I mean over the size of it. Those are unit vectors. So we are getting rid of the size. So maybe let's do steps. I think it's going to be good for you to have steps. Step 1, find R prime. Step 2, you can right away find t, unless you want to have sub-steps to find the size of it, magnitude and stuff. Step 3, you can right away find unit n, and then from now, you go to B. B requires more calculations. Yay! B is the hardest one because now it takes those two and finds a cross product of those two, which is the matrix, and in this case it will be full of trigonometric functions. Oh well, let's do that. What is determinant of the matrix? So it have some space between this bar, before that bar, I, J, K. Now I'm gonna put these vectors here. By the properties of the matrices, you can actually take out of 1 over 1 squared of 2. Because the matrix says, if there's a number, determinant actually says, not the matrix. If there's a number in front, you can multiply it by this number, some kind of row. Or you can keep it inside if it's too confusing. That is fine. But you see, we took it out. And now we're going to have green one minus sine t, well, that's not enough space, minus sine t, cosine t, and 1, and minus cosine t, minus sine t, and 0. I, J, K, like so. And you calculate that. What do you think about this before I move on? Yes? Normal, t prime over t prime. That's how I would remember. Binormal?
No, canceling out like the 1 over x.
Oh, you want details? I see. You actually like asking to explain it. Yeah, that's good. Yeah, maybe it's a bit too messy. I was trying to make it nice. So let's see. I did for n, you have to find t prime. I did it in blue. I found derivative of this t. Derivative gave me 1 over square root of 2. That's a constant in front. Derivative of minus sine, minus cosine. Derivative of cosine minus sine. Derivative of 1 is 0. So this is how I get the numerator. And then you divide by the size of what I just found.
My question was, how did the 1 over x get in the denominator? That was my question.
How would you, can you repeat again?
How did 1 over x get in the denominator, or was that still part of it? That's part of t. Okay, got it.
Thank you, yeah. Okay. Sorry, yeah, I was thinking, zoned out for a little bit. You see? Did he answer your question?
No, he got it.
Thank you, yeah. Good job. Good job for catching up. Nice. See, I should actually just made a trick. Like, does anyone else know how to answer? Then someone would answer. That's nice. Okay, and then you do that thing. You do that thing which we know how to do, which is kind of a long process, but you know, it works out. I just wanted to like motivate you with this picture. This is basically a homework. Tangent vector, normal tangent vector, binormal vector. That's the motivation, 10.8. But you don't see. See, that's what we do. We put on the test questions like this, T and B, and sometimes we put it in the final again. Find T and B, and there's like, yes, that's like all the process is pretty long. But you do the process. However, do you know what's the good news about this chapter? It has 4 problems. So I just spent like an hour explaining it because the theory is important, but actually the homework is not too bad. And then the next one, let's see the next one. That is fun and short. So you'll finish fast. You can finish it basically without me actually on Wednesday or Thursday and start preparing for the test. That is good. Right? See? How nice. Okay, let's do that. 1 over square root of 2. I, J, K. See, it's nice to wake people up with good news. This last homework is actually really fun. Derivative, acceleration, integration. That's the one I like a lot. So I think you will like it. Try to finish it. I think you can do it by Thursday, and then you'll have 4 days, 5 days to prepare for the test. And my practice exam is really good. If you're late for the class, I have a practice test. Okay, the practice test. So I, J, K, we know that. I takes this cosine times 0, 0, yay. Minus sine times 1. That gives you plus sine. Let me write down. 0 plus sine t. Done. Minus j, remember the formula. Usually people do plus, minus, plus. Do you remember? Minus j. Sine times 0 is 0. Minus negative cosine times 1. Same situation, but with cosine. Gives you 0 plus cosine t. Too fast, or should I? It's nice to review before the exam. Yeah.
Let's say something like this with a pure and multiple choice. Can we use the graphing calculator?
Yeah, you can use graphing calculator for anything you want. But usually, cross product is not part of the multiple choice. Oh, maybe it's there. I did not check yet carefully.
Even if it's not in multiple choice.
Oh yes, you can use graphing. You can use calculator.
So do we need to mention that we use the graphing calculator to find the determinant?
So the question is, can we use graphing calculator to skip all the steps? If you know how to do it, yeah, you can do that. The answer should be a vector, remember that. K is, the last one, it doesn't have zeros, but it will just collapse nicely. It's sine squared t plus cosine squared t. And then huge brackets, because there's a factored out 1 over square root over 2. And the answer collapses nicely into this. Let's write it down. 1 over square root of 2 is multiplied by sine t. Let's write it down in the vector form. So it's going to be a vector, comma, minus 1 over square root of 2 multiplied by cosine t, comma, sine square plus cosine square is 1, so it's just 1 over square root of 2. Vector form. So this is my B. B was found as a cross product of t and n. So do you know what I just did, right? I, J, K. That's what we're doing here. What do you think about that? Can you do that? So did you learn how to use graphing calculator to find the determinant? This IJK? So yeah, so the question is, can we do it without showing you steps? Yeah, you can do it. The exams are long in this class. Every time I can see she's making them too long. I will try to make it shorter, but if whatever can help you to speed up, that's definitely you can do that. Yeah.
Could we leave the 1 over square root of 2 like outside of the vector?
Yeah, you can. Good question. Thank you. You could. This one I feel like it looks nicer, but doesn't matter too much. This tells you don't abuse Wolfram Alpha, but hey, did you know it can calculate all of it by yourself? So there was a question here, find TNB at 101. So what do? You plug equal whatever they gave you, t equals 0, 1, 101. And then what I wanted to show you that Wolfram Alpha is nice. I mean, there are other tools like Desmos and of course MATLAB and R. They can do it too. But look at this. Wolfram Alpha is nice. You can actually find all of this. It calculates the determinant. Here it is. Gives you the result and even plots it for you. That's what I like with Wolfram Alpha. Wolfram Alpha using code called Mathematica. And then we're going to go to double integrals later actually in this class. So we're going to learn that too. What do you think about this? Because the last 15 minutes I want to start next chapter to show you it's not too bad. But before we move on, what do you think of all of this? Let's look back. As always, all my notes are posted and my videos are also posted. So you can review that. Let me finish this video on this picture. What are your spines doing right now? Straight up, straight up, straight up. Do you want this? Do you want high curvature? I don't think so.